So today I will tell you about some work we did roughly a year ago with my team at MSR. So the first author is Zhang, who is currently our postdoc, Arturs, Backurs, Ronen, Eldan, Suriya, Gunasekar, and Wagner. And this is about transformers and trying to understand, what the hell are transformers doing. So this will be, what we are going to talk about today. And the way I want to do it is that I want to spend, 15 minutes reminding everybody what are transformers, okay? Just like explaining this architecture very simply. So it might be boring for, the many people who already know exactly what transformers do, but I just want to make sure that we're all on the same page. And then I will tell you about Lego, which is a task that we designed to really understand the training dynamics of gradient descent on transformer. Okay, so that's the plan for the lecture. I will then give you a bunch of experiments on Lego and some of the insights that we can draw from it. All right, but first, what is the context for this talk? The context for this talk is this picture and this New York Times article from like a month ago. So the title is "We need to talk about how good AI is getting." And this is partly what we're going to do today. And this picture, it's a picture that was produced by DALL-E 2. Of course, all of you by now know DALL-E 2. So this is a model from OpenAI that takes as input text and that gives you as an output an image corresponding to the input text. And this image in particular was produced with the words "infinite joy." Okay. And to me, really, like this picture is really shocking. I mean, this result is absolutely shocking. I think it's, in the many years that I've been in machine learning, I have never seen anything quite like that. And to me, there are really two salient points, two things that really impress me a lot. The first is that it seems like the system understands those concepts of, infinity and joy. Like these are very abstract concepts. Yet clearly, it's able to understand something about it, to produce this image. And more than just understanding those concepts in isolation, it's also able to manipulate them, to mix them. It has this kind of, compositional generalization. Not only does it know, different items, but it knows how to put them together. Okay, and I think it's fair to say that nobody really in the world understands what's going on. How is it possible that, these transformers, this neural network architecture, trained with gradient descent on a bunch of images with captions, how can they lead to this kind of understanding? This is a big mystery of our time, and we want to try to solve it. Okay, good. So now this is all I will say about the background. Now let's get into it, and of course all of you know what's going to be on this slide, but I just want to pinpoint what I think are the key element of the machine learning pipeline, and this will just make sure that we're all on the same page. So traditionally, in neural network learning, you have a single input like an image X, a high dimensional vector, and you have your neural network, which is just a function parameterized by some theta in Rp. Okay, P is the number of parameters, and that produces an output given an input, a real output. Now, the way neural networks work traditionally is that they just alternate linear operation with the simplest possible nonlinear operation, which is just the positive part. Okay, so this you guys all know, you have a matrix W1, you multiply your input X by W1, then you take the nonlinearity sigma, and you keep repeating those observations. Now, as all of you know, you train those things by just looking at how sensitive is the output as a function of any parameter in the network. And then you use lots of data to train this, meaning, if you have an image with a pig and your output is, let's say, if it's bigger, then it means there is a pig. So when you see a pig image, you're just going to move all your parameters so that your output gets even bigger. Okay, that's what training is doing. Now, in the last, couple of years, there is one additional ingredient that has been added, which is absolutely fundamental. And where, the point of this slide is really to introduce this last bullet point, which is non-standard from the perspective of, the history of machine learning, which is pre-training. So what is pre-training? Pre-training is you want to solve some very specific task, like the one that I will tell you about later, Lego, which is just solving like high school type systems of linear equation. So you have some task like Lego. What you're going to do is that you're not going to train a neural network to solve Lego. You're first going to pre-train. You're first going to train a neural network on a huge corpus maybe, you know, you're going to try to train on all of Wikipedia, trying to predict the next word on all of Wikipedia. And then once you have this network, which has now been pre-trained and is very good at, you know, predicting the next word on Wikipedia, then you're going to fine tune, you're going to feed in the tasks that you really care about, and you're going to slightly change the weight so as to solve the tasks that you care about. And this paradigm is extremely successful. Okay, this is, you know, what has made all the advances possible in the last few years. All right, very good. Now, so pre-training is one key new element of the last, you know, 5 years or so. But the really, you know, another really important one is the transformer architecture. Okay, so on this slide, I will, you know, give you the gist of what is a transformer architecture. So we have seen just on the previous slide that classically neural networks, they process a single high-dimensional input, like an image. Now, what transformers do is that at a very basic level, instead of working on a single high-dimensional input, they work on a set of high-dimensional input. Okay, so now you have x1 through xn. Okay, now sets, as you all know in this room and, you know, online, sets are a very powerful level of abstraction. I mean, it's very deep down, you know, in the foundations of mathematics. It's just a very useful abstraction. For example, you know, natural language is, you know, you can view it as a set, because a sentence is just a set of words together with their position. When you're trying to do reinforcement learning, you know, you are in an MDP, in a Markov decision process, you have this triplet, state, action, reward, and you have a sequence like this. Another example, of course, is, you know, graph data. You know, for example, if you're thinking about protein folding, like an AlphaFold, etc. So there are many, many applications that get unlocked once you start to think about sets. Okay, and again, this will be just the last point about. I see that pizza has arrived. Hopefully, people are not just leaving because you know, this is too trivial.
Yeah, that's correct.
Yeah, no, it's fine, it's fine. So, what was I saying? Right. So this is just one more bullet point on the background, which is that, you know, in the last 5 years, transformers, but more than just transformers, very large transformers have really revolutionized all of those fields, you know, NLP, RL, you know, any physics-based question, you know, generative modeling, all of those things. And, you know, when I say very large, here is what I mean. In this picture, you know, we're not going to talk very much about emergent behavior in this talk, but this is what I mean. So again, this is also a text-to-image model. This one is by Google, and the text is a portrait photo of a kangaroo wearing an orange hoodie and blue sunglasses, standing on the grass in front of the Sydney Opera House, holding a sign on the chest that says, "Welcome, friends." Okay, so quite a mouthful. And you can see that they have trained different sizes of neural network. 350 million parameters, 750 million, 3 billion, 20 billion. And you see at 350 million, the kangaroo is kind of a little bit cheapish, but at 20 billion, it's kind of very stylish, you know. Moreover, you can read, you know, the words on the sign. Everything is crystal clear. You know, before that, the words don't make sense on the sign. Notice that at 3 billion, for example, the kangaroo has 3 hands. Okay, so this I won't address really in this talk, but this is something everybody wants to understand. What is going on with this picture? You know, how is it possible that when you scale up, suddenly the model gets so much better? Okay, nobody knows. All right. So the, you know, one disclaimer that I need to make about this talk is that I'm doing an extremely bad academic practice of not citing anything. And this is, you know, kind of non-standard for me. The problem is, in this community right now in deep learning, there are thousands and thousands of papers getting published. So it's kind of impossible to do a proper, you know, literature review. It was very different when I was working on Bandit and we were, you know, 10 people in the world doing, you know, the kind of thing that I like. Here, it's really much more difficult. So please forgive me for not citing things correctly. Now, the one citation I have is this paper, Attention is All You Need, which is, of course, the one that introduced the transformer architecture. Now, what is the transformer architecture? I will now explain it clearly. So matrix multiplication is nothing but testing against a bank of fixed filters. What I mean by that is when you have a matrix W with rows, little w, then multiplying by this matrix is nothing but taking the inner product between the rows and, the input X. So for example, when you're trying to, use a convolutional neural network to see if there is a pig to see what kind of animal is in the image, then presumably there is a neuron that tests for whether there is a cat, there is a neuron that tests for whether there is a pig, and so on and so forth. And these are represented as high-dimensional vectors. Now, the key leap, what makes the whole difference to me, is that in transformers, you don't only compare to a fixed set of filters, but you compare part of the input against another part of the input. Okay, and this comparison is done in the attention module. Okay, and this fact of comparing one part of the input against another part of the input, to me, this has philosophical consequences. This is really what makes it able to do reasoning. This is the starting point. Once you start to make, comparison and analogies and abstract away some of the details, this is how you get, to reasoning. So really, to me, this attention module, it turns those neural networks into relative machines rather than absolute machines. And this is why, I think it's such a leap once you start to train those things. Now, how does it work precisely? Okay, so on this slide, I will give you the full definition. Okay, it's actually very, very simple what transformers are doing. So precisely, you have this sequence of tokens. Okay, x1, x2, up to xn. These are high-dimensional vectors. Maybe they represent, for example, a word in a sentence together with its position. Now, each word in the sequence, each token, is going to define a probability distribution over the other tokens. Okay, so let's look at token xi. It's going to define the distribution alpha superscript I. Okay, now how is this probability distribution defined, and what is the meaning of it? The meaning is really an attention distribution. It's telling you how much attention token xi is giving to any other token xj. So the probability that token I gives to token j is going to be something that's a function of a score, and the score is nothing but the inner product between the two token representations. So you take xi, which is your query token. You're trying to look at xi, how much attention it gives to the other guy. And then you look at xj as a key token. You look at how much it correlates with xj. So you take this inner product. Now, of course, this could be a negative number. You put it in an exponential so that it becomes non-negative. And you renormalize so that all of those things sum to 1. Okay, so this gives you the attention distribution. Now, given this attention distribution, I will now tell you how the set of x1 through xn is being transformed into a new set, x1 prime through xn prime, right? Which this will be the attention module transformation, moving from a set of tokens to another set of tokens. And the transformation is kind of the simplest you can think of, which is you're just going to replace xi by a weighted combination of the other tokens, where the weights are just given by this probability distribution. So xi is replaced by the sum of the alpha j xj. That's it. This is the attention model. This is one attention head. Now, of course, we want to train those things. This is a parameter-free, attention module. So the way you make it parameterized is that we're just gonna, just like in classical neural network, we're just gonna add various linear operations. And we're gonna specifically add one linear operation on each occurrence of a token. There are 3 occurrences of tokens. There is xi, which again is viewed as a query. There is xj here, which is viewed as a key. And there is the xj in the weighted combination, which you can think of as a value. You're recombining those values. Okay, so to parameterize an attention head, you just add 3 linear operators. One on this xi, one on this xj, and one on this xj. Okay. Now, what are transformers? Transformers just alternate between these attention heads, and in fact, it is doing many attention heads in parallel. Okay, so it's a multi-head attention. So it's doing many attention heads in parallel, which are then being recombined with another linear operator. Okay, so this is a multi-attention head, and then each token separately is being processed by a feed-forward neural network. And just on top of that, you also add residual connections and normalization, and this is it. This is a transformer architecture. Okay, so maybe maybe I can take a question here if there is a question, and if not, I will move to just a pictorial depiction of what's going on. But is there a question on this slide? Okay, I guess everybody knows about it. So here is just, to make sure we're all on the same page. So here is a sentence. I think AGI might be near. And, these are high dimensional embedding for all of those words and positions. So, X1, X2, X3, X4, X5, X6. Now, the attention module is going to transform this set of, Xi into another set where, X3 is just going to be replaced by a sum of alpha I Xi, where the alphas are, again, this attention distribution that I defined on the previous slide. This is parameterized by these three linear operators that I told you, WQ, WK, WV, which is query, key, and value. Now, in fact, you do many of those in parallel. Okay, so your set of tokens is being sent in parallel to all of those attention heads, is being processed. You have a residual connection and a normalization. And now each token is being processed independently by the same feed-forward neural network. You again have a residual connection and a normalization. This is one transformer layer. And now you stack those things up. One attention layer, two attention layer, and so on and so forth. And for example, if you want to do classification, let's say you want to do sentiment analysis, you have this set of layers. And then you also have maybe a CLS token, a classification token. And at the end, after being processed by however many layers of transformers that you want, you just add a linear classifier layer on the CLS token, and that will tell you whether it's a positive or negative sentiment in the sentence. Okay. Now, it turns out what I'm glossing over is that it's not so easy to train those things. Okay. So you have to be a little bit careful. I didn't talk about what is the optimization algorithm that you use exactly. It's not actually exactly SGD. How do you tune the learning rate and all of those things? And once you get to very large scale, like many billions of parameters, you need many GPUs to work, together, etc. So over the past 3 years, there is really an industry that has been developed around training large transformers. And that's why now they are famous transformers. Okay. Those are famous transformers just because it's not easy to produce these artifacts. Okay. So here are some examples, and I will tell you, this will also give you a picture for those of you who are not in this field of what kind of research is going on there. So to me, the most important one is BERT. So BERT was trained on mask language modeling, meaning you just, you have a sentence in natural language and you hide, maybe 10% of the words, you replace them by a mask, and your task is to unmask them, to discover what was really behind the mask, okay? So the BERT model, it has depth 12 layers, it has 12 attention heads, and the dimensionality of the embedding for the tokens, okay, so for the English vocabulary in this case, is 768. That amounts to a total of 110 million parameters, and it's roughly divided, 1/4 in the attention modules, 1/4 in the embedding at the very beginning, and the rest, half of it, is in the feed-forward, the 12, you understand there are 12 feed-forward in BERT. GPT, of course, all of you have heard about it. GPT, it's slightly different from what I talked about because it's a decoder-only architecture. The detail of this really doesn't matter for this presentation. What's maybe more important is that the task that it's trained on is predicting the next word instead of mass language modeling. Now I will tell you some variants, which I like, and give you a sense of what kind of research has been going on, I would say, between 2017 and 2020, which is to try to make modification to the architecture. So here is one that theoreticians usually really like, which is Albert. So Albert is BERT, except that you keep repeating the same layer over and over again, okay? So if you want, you just weight tie all the layers. And that makes sense in theory because, we like to apply, we like things to be simple, to apply the same operation over and over again. Another example of a modification, which is along another axis, is Roberta, which is a better trained version of BERT. And again, this points to the fact that training those things is not easy, and we don't know if we have the optimal way to train them by any means. For example, Roberta was trained with a larger mini batch. Now, the scale of BERT is way outdated, really, really outdated. So here is the biggest, Microsoft model, at least the biggest publicly known Microsoft model, which is Megatron Turing. So here you see we make a jump. Now we have 105 layers, 128 heads, 20,000 dimension for the embedding. That amounts to a total of 530 billion, parameters. And this was trained, to give you a sense of scale, on 3,000 GPUs, A100 GPUs for 35 days, using 270 billion tokens. Okay. And now, for example, we know that this is a very bad trade-off. I mean, that many parameters for that few token is not a good idea. You should rather have, 500 billion token and maybe 500 billion parameters and 5 trillion tokens. Okay, but this, 2 years ago, this is what was trained in Microsoft. Okay, and many other famous one, like Clip, DALI, Copilot, and so on and so forth. Okay, great. So this is all good. This sounds like a lot of fun, but there is a tiny problem, which is nobody understands what's going on. Okay, really, truly. And here, again, to an audience of theoreticians or people who are grad students, like, it's really important for me to convey what I mean by understanding. In the context of convex optimization, you can understand gradient descent. If you're Cauchy, 2 centuries ago, you understand gradient descent because you know calculus. And you know that, locally a function should be linear. So that makes sense to move, in the direction of the gradient if you want to minimize your function. If you're in, in the 20th century, understanding is not, you don't need to just know calculus. You actually have to, understand the rates of convergence. You have to be Nesterov and discover, accelerated gradient descent. Here, when I say nobody understands, I really mean nobody has a calculus, to understand those things. We're not at all talking about rates of convergence or anything like that. So it's really, that's what makes this field so exciting, is that it's really very deep down in the foundation that we don't understand what's going on. We really have to redefine, I think, everything. Now, here are some very concrete questions. What are those attention heads doing? I mean, you're telling me, like in Megatron Turing, there is 100 layers and 100 attention heads, so you have 10,000 attention heads. What are those 10,000 operators doing? Are they all necessary? Here is a basic question. Why is pre-training so spectacularly good at transfer learning? Here's one thing. The first time I heard it, I was really shocked, which is some people wanted to train a reinforcement learning agent in the OpenAI gym, whatever, some cheetahs that had to run or something like that. And to do that, they first pre-train their transformer on Wikipedia. And, I asked them, like, what the hell is going on? Like, why do you think, pre-training on Wikipedia is going to help, your cheetah run faster? And they were like, I don't know, maybe the network is going to run, is going to read some article in Wikipedia on, how, motor cortex work or something like that. And I was like, okay, this doesn't make any sense. But still, it works. It really works. So we want to understand what's going on there. One thing that I briefly touched upon is the emergent behavior. So this is really, absolutely incredible. And, this was the picture that I showed you of the, kangaroo at 350 million parameter and the kangaroo at 20 billion parameters. These are not the same guys. Okay, so it's really, really impressive. This is a slide that usually comes with it. Maybe I can, during the Q&A, if you want, we can talk about this more. I don't want to talk too much about it right now. Of course, related to emergent behavior, what happens if we keep scaling up, and there are some safe AI consideration. Again, if you want to talk about safe AI, I'm happy to do it maybe after the presentation. Overall, I would say everybody is lost. And I think we really need to go back to things that are a little bit simpler and try to, go a little bit more slowly to try to get some actual solid insights, okay? And I don't want to go as slow as I go when I do mathematics, okay? I don't want to prove things. I want to have a more like physics type approach where we do experiment and we try to see, how do the various parts of the architecture orchestrate together to get you the result, okay? So it's not science of deep learning. It's not the mathematics of deep learning. I would say it's the physics of deep learning. It's a slightly different take. This Lego data set, here I write that we use it as a microscope into the dynamics of transformer. I don't think by any means that Lego is the ultimate microscope in any way whatsoever, but it's a starting point. And you will see that even with a silly starting point like this, you get a lot of insight. but there is just infinitely more that you can do here. Okay, so let's jump into it. And before I jump into it, let's see if there is any question at this point. Okay, you guys are ready for some experiments, I see. All right, let's do it. So here is LEGO. So LEGO stands for Learning, Equality, and Group Operation. And it's much more general than what I write on this slide, but the generality really doesn't matter at this point. And we can talk about it maybe after the presentation. In essence, LEGO is really like high school type systems of linear equations, okay? And in fact, it's even like very, very simple high school type where you just have a chain of reasoning that you have to follow. So here's an example. You have a set of variables, A, B, C, D in this case, and you have linear relationship between them, which are just, whether one variable is equal to plus the other variable or minus that variable, okay? So for example, B, I tell you it's equal to minus A. D is equal to minus C. C is equal to plus B, and you see A is special. A, I anchor it to be a value, okay? So A is equal to plus 1. So how do I resolve, this thing? I just see, okay, A is equal to plus 1. Then I move here. Okay, so if A is equal to plus 1, that means B is equal to minus 1. Then I move back, to the end. If B is minus 1, then C is minus 1. And so D is plus 1. Okay, very simple chain of reasoning to be followed. Now, what we want to do is we just want to train a transformer on sentences of this form. Okay, and I'm going to call the length of a sentence. It's just going to be the number of variables in that sentence. Okay, so here this would be a sentence with 4 variables. So I have a transformer. I have a high dimensional embedding, for all my variables. I have a high dimensional embedding for the equal sign. I have a high dimensional embedding for, the colon. I have a high dimensional embedding for the plus sign, for the minus sign. Okay, so this gives me a sequence of tokens. I'm going to have a BERT transformer, which is, like just the architecture of BERT. And I'm going to train from scratch. And then I append, a linear classifier on top of each variable token at the end to tell me whether it's a plus 1 or minus 1. Okay. And what I like about LEGO is that it really surfaces, 2 key operations that you need to do when you reason. One of them is that you need to be able to associate concepts. And what I mean by that is, look at this sentence. When I say A is equal to plus 1 here, and when I say B is equal to minus A here, of course, we understand that A and this A, these are the 2 same concepts, and they need to be linked. They need to be associated. The transformer, though, does not really know that, because what does it see? This is, of course, a transformer is, you have a high dimensional embedding for the symbol together with the position. So this A is in position, whatever, 7 or 8, and this A is in position 1, 2, 3, 4. Okay, so this A is in position 4, and this A is in position actually 11. Okay, so the 2 high-dimensional embedding are not the same. These are not the same vector. So the network needs somehow to understand, okay, actually, there is a positional encoding part and there is a variable part, and the variable part needs to be associated. I need to realize these are the same things. Okay, I also need to be able to manipulate my concepts. So not only do I associate the 2 A's, but also when I realize this A is a plus 1, I have a minus in front of it. So I need to see that the minus concept, when it's applied to a plus 1 value, this gives me a minus 1 concept. I need to be able to do those local manipulation. Okay, and we'll see how transformers learn to do this association and local manipulation. Okay, now the point is, association and manipulation are very easy to implement with attention. So let me explain this, and then we'll see whether, gradient descent trained on transformers actually learn this easy way to implement it. So here is how you can do association. It's very, very easy. Let's say you have 2 occurrences of the variable z, okay? And let's say right now their embedding are alpha plus beta and alpha plus gamma. Maybe beta and gamma are the positional encoding of the 2 different positions of z, okay? And let's say no other token contains alpha, because alpha is actually the high dimensional embedding of z. Now let's see. It's kind of obvious that by high dimensional concentration, what's going to happen is that the inner product between alpha plus beta and alpha plus gamma is going to be of order 1. Remember, everything is normalized, so all my vectors are unit norm vectors. So this inner product is of order 1 because they both contain alpha, but the inner product of alpha plus beta with anything else is going to be very small. It's going to be of order 1 over square root d, because those are kind of random vectors which are almost orthogonal to each other. So you see in my formula to define attention, the two occurrences of z, they are going to attend to each other. You know, the first occurrence of z alpha plus beta is going to put most of its attention on alpha plus gamma, provided that I have an attention head for which WQ and WK are the identity. Okay, so one token mostly attends to the other one, to the other token of z, assuming that, you know, WK, WQ, and WV are identity. And in fact, in this case, you even transfer the information. So after one attention head like this, you know, alpha plus beta will become 2 alpha plus beta plus gamma, because I have pulled the information from the other guy. Okay. Now for manipulation, it's also very easy to do it. So what you can do is you can do a local convolution. And this is really important to understand. I don't know why people are not using more convolution in natural language processing, because convolution makes total sense. I mean, there are some local operations that you want to do. So in this case, if you have an attention head that does a kind of local convolution, meaning its attention is really focused on the positional encoding part and saying anything which is close by, I average, and anything which is far away, I just do not consider. Then what will happen is in the B equals minus A, in the B token, I'm going to put the minus and I'm going to put the A. And then I can use the fully connected feed-forward neural network to do the manipulation itself. I can have a neuron, you know, that says if I have a minus and a +1 value, then what I should output is a -1. And note, for example, here for the expert in the room, notice that the sentence I just said is particularly easy to implement if you have gated linear units. I know this is an important sentence in a way, because in the deep learning community right now, people think, you know, oh, you know, gated linear units, they work better, but nobody can understand why. In fact, in a paper by Noam Shazir, with, you know, one of the people that I really respect in this field, he has written a paper, a 5-page paper on how gated linear units are just so good with transformers. And the last sentence of the paper is like, as with anything in deep learning, we can only, you know, praise the deep learning god that this is working, and there's no way we can understand. It's not true. It's not true. We can actually understand what's going on, but it's not an easy answer. It's not like, you know, the convergence rate of gradient descent on convex function. It's really a much more delicate matter, but not impossible. Anyway, okay, so now finally, you know, after 35 minutes, a first experiment, a first plot, the first real thing. So we are now going to train a BERT architecture on Lego sentences. We're going to train it on Lego sentences with 12 variables. Remember, a Lego sentence looks like this: A equals +1, B equals -A, etc. This corresponds to a chain of reasoning, where the first node is a 1, let's say, +1. Then each edge is labeled with either plus or minus, and each node has a variable, okay? Now, there is the order of the variable as they appear in the sentence, and there is the order of the variable as they appear in the chain of reasoning. These two things are not the same, okay? So here A is first in both, B is second in both, E is third in both, but F, you see F in the chain of reasoning, it's the fourth variable that appear, but in my sentence, it's not the fourth variable, okay? So this is important. Now I'm going to number variables as they appear in the chain of reasoning. Okay, so variable 1 is A, variable 2 is B, and so on and so forth. All right, so we're going to look at a bunch of plots like this, where on the x-axis, it's the number of epochs of training. On the y-axis, it's the test accuracy. Okay, so it's the accuracy at test time. And here you see I have trained on 12 variables. Okay, so from variable 0 to variable 11, and I'm showing to you the accuracy, you know, for each variable as you keep training. And you see, you know, first of all, first thing you see is that they all shoot up to 100%. Okay, so transformers, they just learn to solve these systems of linear equations. They learn to solve Lego, and they do it very well. You can also see that it does it very naturally. Like, you know, the first variable first jump to 100%, then the second variable jumps to 100%, then the third variable, and so on and so forth. Okay. okay, great. So should we just, go home and, transformers solve Lego and it's wonderful? Well, let's wait a second. Let's try to test whether transformer really understood what the task is about. And to get to this, really understand, what we want to do is we want to test it out of distribution. So the way we're going to do it is I always want to have variables, like Lego sentences of length 12. We're always going to have 12 variables. But what I'm going to do now is that I'm going to train my BERT model, but only by providing supervision on the first half of the variable, on the first 6 variables. Okay, so in this, like the picture will be like this. Let's say I have here I have a sequence with 6 variables. The first half is just the first 3 variables. So I'm only getting, the transformer is only getting a loss on variable A, B, and E. It's not getting a loss on F, D, and C. So this is really a type of length extrapolation. I've been trained to solve, systems of linear equations with 3 variables, and now I'm being tested on systems of linear equations with 6 variables. Notice though that I'm being a little bit clever and that the positional encoding is not an issue here because I always feed full sequences. Okay, so it has seen all the position, and because I randomly shuffle, the clauses, all the position have mattered, it has learned to do the positional encoding everywhere. So now let's see. Now the next part I'm going to show you, there will be plane curves, which are the variables that it has seen at training time, and there will be the dashed curve, which are the variable that it has to extrapolate over at test time. And this is what happens. It fails miserably. Okay, so transformers do not understand at all what the task is about. If it has been trained on the first half of the variables, they jump to 100% at test time. But even just one more variable 6, the 7th variable, it barely gets to 70% accuracy, and after that, the rest is just random chain. Okay, so transformers do not extrapolate at all. Okay, now, of course, this, if you take the classical learning theory perspective, this is not at all the end of the story. What you want to do is you want to say, okay, what I need to do is that I need to modify my architecture so that it has a better inductive bias. Okay, because at the end of the day, even though this is not a term that you hear a lot of people talking about it in deep learning, it's still a very real thing. Of course, inductive bias matters, How do you extrapolate from what you have seen at training time? This is obviously a very real thing. Now, here is the experiment we're going to do. Notice that when a human solves a system of linear equation, like this, you really do a for loop, right? You really replace one variable one by one, right? Gaussian elimination, okay? So in essence, we're asking the transformer to learn a for loop. Now, a for loop, what about, doing something like Albert, where you weight tie all the layers? Okay, that does seem to make sense. It has a more inductive bias towards the kind of solution that we want to see. So could it be that on Lego, Albert does much better than BERT and actually learns, to extrapolate? So let's see what happens. So on the top, you see when we have trained on length 12, okay, fully trained on all 12 variables, and both BERT and Albert, they get to 100% everywhere. Now let's see what it does in terms of extrapolation. So, okay, BERT does not do very well at all, but look at Albert. Albert is doing amazing. It gets to 100% to one more variable. It gets to 100% to 2 more variables, and it's starting to go up for 3 more variables. Okay, so it did get what it is, supposed to do. Albert just works much better than BERT on Lego. And note that Albert has much fewer parameters than BERT. Okay, it has only 30 million parameters. In fact, most of the parameters are in the embedding. Okay. Is there any question at this point?
Yes, there's a question, but.
Hi, I have a question. So I was wondering, in that last bottom right graph, you can see that there is continuous improvement on the variables without loss. I guess with 3 more variables that happens after it seems like the variables with loss have already converged. So do you have any idea what's going on there?
Yeah, yes, I think I do. But it's non-trivial. So I think what's happening is that basically, it only knows how to solve 6 variables, but then, it can extrapolate a little bit because it can handle the extra noise that it gets from, repeating the operation one more time. Now, as you train more and more, it gets better and better at cleaning the noise because, you're training with the logistic loss. So maybe this is, something that is important. You're training with the cross entropy. So there is always value in reducing as much as possible the noise in the network. So in principle, it is possible at least that this curve, if you keep training forever, maybe it will get to solving all the 12 variables. Now, what would be much more crazy is if it could go beyond 12 variables, because notice that it has only depth 12. And I will comment on that at the end of the presentation.
Yeah, go ahead.
Can I ask a question?
Yeah.
So is there any evidence of like the depth of the Albert architecture relating to like the number of steps that you have to perform in the chain of reasoning? So if it's 6 steps, do you have evidence that like a depth 5 Albert would not work, but like a depth 6 would work or something?
Yeah, absolutely. So we do have evidence. So in the paper, we do, what we do is basically we do linear probing at every layer to try to see how early, can you resolve any variables? And you see a very clear linear trend. So, the first few variables are resolved in the first few layers, and so on and so forth. Now, so this is what we have in the paper, and it's a true, plot. Now, let me, cut to one of the conclusions is that during the summer, Yintat Lee trained, a network like this, a BERT model, but he trained it to solve Lego sentences with 50 variables. And it works great. So, 50 variables, you cannot just do a for loop, like it's learning something else. So even though, I do think that the network we have trained in the Lego paper, they do learn the more natural for loop, it seems that those transformers, they definitely have enough capacity to do something much better than that. And they can find it. So I see in the chat there was another question about the order, and maybe there is a question also in the room. Yeah.
You want to go first?
Yeah. Did you do any tests to see if the Albert could generalize to having more layers applied at test time?
To having more what?
Like having a larger depth at test time. Like you trained it with depth 12, but then could you run it for a higher depth?
Yeah. No. Very nice. Very nice. Beautiful question. No, we did not try, but this is very natural. My guess though is that it's really gonna, my guess is if you keep training, then eventually it can handle repeating itself, but it's not clear actually. But it's a great question. So in the chat there was another question about the order in which the variables are resolved. The fact that it's first variable 1, then variable 2, and so forth. And this is a great question. I want to point you to this graph here, the upper right. So you see it's first variable 1, then variable 2, but then look at this. It's the last variable that starts to go up. And you see as the last variable starts to go up, the second variable starts to go down. So what is going on? I think you have to look at those graphs and try to understand what's going on. Why is it that the last variable starts to be resolved, before any other one? Is there any guess? So again, the point is, you have this thing which is trying to learn how to process a chain of reasoning, and it first understand, okay, I first have to resolve the first variable, then I have to resolve the second variable. And somehow this guy, Albert, it now says, oh, actually, I also know how to resolve the very last one. So what happens is that there is a trick. There is a shortcut, which is the last variable. You can just take the product of all the signs in the chain. You can just count how many minuses there is in the chain, and the parity of the number of minuses will just tell you what is the value of the last variable. So this guy, this Albert, has learned the shortcut. it's a very bad shortcut. Like it's a great shortcut, you know, if you want to solve the task at hand, but it's a terrible shortcut in terms of extrapolation. And you see, Albert here, it extrapolates great. So what's going on? Well, what's going on is here in the top one, it's learning a shortcut because it has supervision on the last variable of the chain. But in the bottom experiment, I'm not providing supervision on the last variable of the chain. So on the bottom plot, it cannot learn the shortcut. So we are not seeing on the bottom plot the terrible, you know, effect of learning a shortcut. So the next experiment that I will show you is exactly the same thing, except we also provide supervision on the last variable. Okay, so we're only going to give more information, but you will see that it destroys the behavior of the architecture. So let's do it. So here, let me see. Yeah. So on the bottom, you know, I'm just providing supervision. So again, I just want to provide supervision on 6 variables. So what I'm going to do is here on the bottom, I provide supervision on the first 5 variables. And on the top, I provide supervision on the first 5 variables plus the last one. And you see, the bottom one looks nice. Everything is going up and, you know, there is some extrapolation. But look at the top one. It gets worse. You see, even though I provided more information, it gets worse. Right. The variable number is a number in the chain. Yes. I see. Okay. Was this clear? So I think it's very important, this point. You really have to understand, like, classical generalization can be very misleading, right? Because you see, if you just looked on the previous slide at classical generalization, Albert was doing great. And we're even happy, like, look, it solves the last variable in the chain super well. That's amazing. But as soon as you take it out of distribution, it collapses, okay? So the thing is, those networks are really good at grabbing onto any kind of shortcuts. And I think this could be related to emergence, to emergent behavior. Because basically what happens is, as you make the task more and more complex, there are fewer and fewer shortcuts to solve. You have to do the real thing if you want to solve the problem. So maybe that's why, you know, making the task more complicated, training on all of the web is so good. It's because it removes all of those silly shortcuts that you would have at smaller scale. Okay, good. So now I want to make a key point of the presentation, and then I think I will conclude. So the key point of the presentation, I will not do this one. The key point of the presentation is really that one, which is, at this point, many deep learning people would be frustrated and be like, what are you talking about? You know, how can you get any insight on what deep learning is doing when you're training your neural network from scratch? Again, the real recipe is pre-train and then fine-tune on your task at hand. So let's see what will happen if I do that on Lego. Okay, so let's take the pre-trained BERT, which was pre-trained on Wikipedia, and let's see whether it does better than the randomly initialized BERT. Now, of course, a priori, you know, I think it's very natural to say this doesn't make any sense whatsoever. How is it that, you know, reading Wikipedia will help you to solve these high school linear systems of equation, unless somehow, you know, there is some magic and those networks really learn, I don't know, learn to solve systems of linear equations by reading Wikipedia. That doesn't seem very likely. But here is what happens. It works amazingly well. It works really, really great. So the left side is a plot that we have already seen, randomly initialized BERT. The right side is a pre-trained BERT. So you see, it shoots up much faster. Okay, it needs much fewer epochs, but also the extrapolation is much better. I mean, it's a very clean extrapolation. You know, it's natural that there is some, you know, degradation in the number of variables. But it works really, really great. So what's going on? Okay, we want to understand. Now, by actually plotting the attention patterns, okay, so the attention pattern is just, you look at a sentence versus itself, and you just plot all the probability distribution, all the attention distribution. Here's what we see by hand, okay, scanning through the attention heads. We see that on the first layer, the third head it has this you know, diagonal bend. What is this diagonal bend? Well, it's a manipulation head that I was telling you about. It's you know, doing the local convolution. It's putting together the information in each clause. Now let's look at, you know, on the second layer, head 11, what is this attention pattern? It's actually the association attention pattern. Okay, it's not clear here, you know, I would have to zoom in and show it to you, but it's exactly that, you know, a token A attends to all the other token A in the sentence. A token B attends to all the other token B in the sentence, and so on and so forth. Okay, so this is at the end of pre-training. This is without, you know, before seeing any Lego sentences. So the question is, you know, are these the manipulation and association head? And are those heads the reason why pre-trained BERT is so good on Lego? Is it just because it has learned the concept of a manipulation operator and an association operator, which is of course less sexy than saying that, you know, it has read Wikipedia and learned to solve systems of linear equations, but also seems more reasonable. So this is an hypothesis at this point, okay? And now we're gonna test this hypothesis. And the way we're gonna test it is that instead of having the pre-trained BERT, we're gonna take a randomly initialized BERT, but in every layer, we're gonna put one manipulation head and one association head, which are just supposed to mimic the corresponding one in the pre-trained model. And let's see what happens. What happens is this. It almost perfectly mimics the pre-training behavior. Understand, mimicking BERT has seen 0 article of Wikipedia. This is a completely, you know, like data-free initialization, where we just make sure that we have a manipulation and an association head in every layer at the start. Okay, so the question at this point is, you know, is this a more general phenomenon? Is it the case that pre-training in general finds useful, you know, general purpose operators, and then those general purpose operators can be fine-tuned? Okay. All right, so let me conclude, and then, you know, I can take questions. So one conclusion, I think, is that those large language models, maybe they are not impossible to understand. Okay, for example, here, I think we were able to quite conclusively understand why pre-training is so successful at transfer learning on Lego. Of course, I'm not saying this particular story necessarily extends to all of the successes of pre-training, but maybe this is an avenue to do more research. Classical in-distribution generalization can be very misleading, okay? Sometimes there are shortcuts, and those transformers are very good at finding the shortcuts, okay? An important sentence, not for this audience, but for other audiences, it's important that people really get that point. Like transformers, they do not have an inductive bias towards human-like solutions. They have nobody understands what is an inductive bias of transformer. It's a fantastic question, but it's certainly not towards, you know, simple human-like circuits. There is nothing like that. I didn't tell you about this, but, you know, I just told you that Albert is better than BERT on Lego, and this makes sense from an inductive bias perspective. But in fact, we did more testing there. For example, stochastic depth works great also, because what is stochastic depth is just you stop the network at a random depth. Now, the point is, if you stop at a random depth, then the network has an incentive to try to resolve the first variables as quickly as possible. So it's really incentivized to go toward the solution, which is solving the first few variables very quickly. Okay, so if you do stochastic depth, actually you get much better extrapolation. Layer dropout is the same story. It works great, layer dropout. In fact, when you move to more complicated Lego sentences, you know, let me just say this, that the Lego sentence I have shown you is on the group of 2 elements, just plus minus operation. But you can do Lego sentences on any group. And when you move to more complicated groups, most of those things that I told you today, they fail. It doesn't train. But if you start to put in layer dropout, then suddenly it works, which is really, really interesting. And yeah, the past summer, you know, we did a bunch more experiments with many interns, and we have, like, you know, really, really, really many findings. I don't even know how to organize them best. For example, one of them I mentioned is, you know, this length 50, in fact, even length 100. So Yintat was able to solve, you know, with just 12 layers depth, 100 variables sentence. And what happens there is that there is another type of heads. I told you about manipulation and association, but in that network, there is a lot of broadcasting head. So these are heads such that, there is one token that everybody attends to. So this token basically broadcasts its content to everybody else, okay? Layer dropout gets better length extrapolation. We have tried, efficient transformers, meaning, instead of having the quadratic complexity, having the near linear time complexity, and they fail, and we know exactly why they fail. We have tried, like, when you have more variable names, what happens to learn a full dimensional attention, etc., etc. There are many, many more things. Okay, I will stop here and maybe take questions. Yeah, there is a question in the chat. Bing Bin.
Hi, thank you for the great talk. I'm just curious, like, so do you have a few more words about the failure modes? So do you know, for example, if it fails to generalize to longer chain? So say if you're training on the first half of the chain and then generalize to the second half. So do you know what is a failure mode? So for example, does it fail to learn the operation or the variable names?
Oh, I see. So, yeah, that's a good question. I mean, in a way, like your prior should be that it will fail. Like it's kind of, I think in Spirit, I'm focusing on the success mode because my base assumption is that it will fail. Like there is no, if it has been trained, if it only gets a loss when it will resolve the first three variables, then a priori, it's very mysterious. Why would it bother to solve the fourth variable or the fifth variable? A priori, there is no reason. So that's why, in my view, a priori it fails. And when it succeeds, we can try to understand why it succeeds. And I think why it succeeds is really because it's kind of more robust, basically, to try to do more variables, to try to repeat the operation, Because again, what is the solution, the human-like solution is to do this for loop where you keep repeating the operation, namely find a variable that has been unresolved, and then look on the right-hand side and try to see if the right-hand side is resolved, and in that case, resolve that variable. And if this is what you're doing and you keep repeating that operation, then eventually you will solve everything.
So it sounds like Albert is doing something similar to that, right? Because we're tying the weights.
Exactly. Yes, absolutely. Yeah.
All right. Thank you.
But then, I just want to say, even though I think the story I told you today is consistent, once you move to like more complex groups or longer chains than the depth, the story becomes so much more murky and I don't know what's going on exactly.
I see. Cool. Thank you.
So there's a question in the chat about what happened when trained with infinite many variables names. So yeah, great. So here is the thing is when you have finitely many variable names, the association, you remember I told you there needs to be an association head, which is associating, A to A, B to B, etc. But if you have only like, the letters of the alphabet, 26 letters, then you're going to learn an association on a 26-dimensional subspace, which is a subspace spanned by those variable names. Now, if you have infinitely many variable names, now you have a chance to learn a full dimensional association, which is what you really want to learn, because the full dimensional association is much more useful. In particular, if somebody comes up with a Lego sentence with variable names that you have never seen, then this will generalize. Whereas, the 26-dimensional association subspace one will not generalize. There is a question. Have you tried using SAM training transformer with random inits? No, so we haven't tried SAM. I mean, there's just, again, I want to go back to one of the points that I made at the beginning, there are really just so many directions that you can take from here. And again, not necessarily only on Lego, you know, there is, for example, a paper out of Stanford that I really like recently about in-context learning, you know, where they have Lego-like sentences, except it's not a system of linear equation. What you're really trying to do is linear regression. Okay, so linear regression is slightly different. Like you get sentences that looks like, you know, pairs x1, y1, x2, y2, etc. And the last one is xn plus 1. And the yi's are just a linear function of the xi. So yi is w dot xi. And what you have to learn, of course, is what is w, and then multiply w by xn plus 1. And they have all kinds of experiments, but they didn't go into, you know, the inner workings of the transformer, trying to understand when it succeeds, when it fails, and why. And you know, this kind of Lego-style study can be done there too. It can be done, again, for different tasks. It can be done for different algorithms. All of this is very, very valid. Are the empirical results mentioned in point 4 available anywhere? No, not yet. Again, it's kind of becoming hard to decide, you know, what to publish, how to organize this knowledge, you know, where is this going? So we're thinking about it, but we don't have anything right now. For layer dropout, yes, we have a very clear intuition, which is here's the intuition. Layer dropout increases the robustness of your network. It incentivizes you to repeat the same operation because some operation might disappear. So you cannot rely on any single operation. It's the same intuition as just, you know, regular dropout, but when it's on the layer dropout, it's really like making a structured, you know, version. And this is the kind of experiment. Maybe I can just show the experiment. Yeah, so this is layer dropout. So this is, okay, so these are experiments on the group S3, okay? So everything I told you in the presentation is about the group S2, okay? So just the unique group on 2 elements, which is also the group of permutation of 2 elements. Now we did experimentation on the group of, you know, permutation on 3 elements, which is very interesting because it's non-commutative. So that means there is no shortcut. Okay, this would take longer to explain, but you see it's very, very different. In particular, we are not able to train randomly initialized networks. Okay, so this we don't understand, we don't know why, but randomly initialized network do not train on this task. If you train the pre-trained one or the mimicking one, they do work, okay? But you see the pre-trained one, it's struggling like crazy to extrapolate. And Albert also, right? They really extrapolate not so well. But if you now take a pre-trained BERT with layer dropout, with 0.3 probability of layer dropout, then it does extrapolate very well, okay? You're gonna tell me, why is it dropping? I don't know, we don't know. You know, we don't know what's going on. Any other question? With infinite many variables, did the network excels at each variable in a sequential way? Okay, very, very good question. Let me think. So as far as I remember, yes, there was no surprising behavior there. It was really more like it was slightly like it failed. Okay, here. There was one surprising thing. So actually, it's very interesting. With infinitely many variable names, starting from random initialization, it was basically a coin flip whether it would train or not, which I find like so mysterious. So there was basically a probability 50% that it would train and a probability 50% that it would not train. And maybe what's happening, is that, you know, with the finite number of variable names, there are many ways to solve the problem, including various shortcuts. But in the infinite variable names, maybe there are no shortcuts. So the shortcut-like solution disappear. And maybe they were half of the basin of attraction, you know, because basically the network either is going to go towards the association solution or it's not going to go towards the association solution. And, you know, in finitely many variable names, both association and non-association, they can, you know, generalize at test time. But with infinite many variable names, only the association one can generalize at test time. And maybe, you know, there's a different mass on those two basins of attraction. And I find this like really, really interesting and mysterious. The fact that it's 50%, you know, like that it's a coin flip. It's not like, you know, 98% and it's not 2%. So this, yeah, is very surprising and we don't understand. So I see there was a question in direct message about, about whether Albert learns an iterative algorithm, but different from the human constructed one, because in the paper, we show, you know, when you do linear probing on every layer, we show that basically Albert needs 2 layers to resolve a new variable. And this could be just because maybe, you know, one layer does manipulation and one layer does association. It's not necessarily like it's clever to do both manipulation and association on the same layer. And so maybe, you know, Albert is not that clever, but it's true. Maybe we need, you know, like understanding, you know, the effect of depth, the effect of various parameters on the question of interest these are great questions. Like even, you know, what about the dimensionality of the embedding? You know, as you vary the dimensionality of the embedding, what happens?
There's another question.
So I have a quick question. So it seems to me like Albert is kind of an extreme version of layer dropout. There's only one layer essentially that's kind of responsible for everything. Do you have any thoughts about the relationship between the results of Albert and the layer dropout and like how they might relate?
Yeah. So yeah, good question. So I think I think I'm not sure how much sense it makes to do layer dropout or stochastic depth with Albert, but maybe it will, what will happen if you do it, then you can repeat more steps of Albert. It becomes more resistant. Like maybe you've trained it to do 12 steps, but maybe at test time you can do, you know, 20 steps. So maybe, you know, this is something that has to be tested, but I think that's like reasonable to expect that. Good question, Bing Min. So she asked, what happens if we supervise on the second half of the variable? My guess is that it's not going to train. But that's a great question. My guess is that it's not going to train. And if we include, you know, expression like the one you say, minus b equals minus a, and this has not been seen at training time, my guess is that it will also fail. I mean, I'm sure, in fact, it will fail. Because you see, it doesn't really know what is a minus sign. It knows what is a minus sign after an equality sign. So if you have equal and then minus, then it knows what to do with that. But if you have a minus, which is at a different place, it has really no reason to know what that means.
Questions from the room? I'm curious how mimicking initialization might affect performance on normal natural language tests more general than Lego. If you've looked into that.
Yeah. So I think it's not yet on archive, but we are testing with a modification to the transformer architecture that would basically have a built-in association and a built-in manipulation. And we're training that on, you know, natural language. So far, our experiment is that we can we redid the BERT pre-training, and we get similar performance, but it's much more efficient with much fewer parameters. So now next, what we have to test is if we equalize the number of parameters, for example, or the computation time, does our new architecture beat the standard transformer? And I think it will, but I think it's not going to be a huge jump. So there's something like in general, it seems to be so hard to beat like out of the box transformer. So maybe we can beat it a little bit, but it's not going to be a game changer in my opinion. But it's a much more meaningful architecture. Like it's much more interpretable because of this built-in association.
Yeah, I imagine it might train faster. Is that the case, even if the final performance isn't necessarily better than a plain transformer?
Yeah, you're totally right. That's exactly what it does. It trains faster. Like you can really see on the pre-training, the curve drops much before, but eventually they both reach the same point.
That's really cool. I'll watch out for it. Any more questions? Okay.
There is a question in the chat. Salvador.
Hi, hello. Thank you for the great talk. My question would be, did you make any ablation study on the variable that it's really close to achieving the test accuracy 1? I think it is variable 7 or 8. Where did it fail?
You mean which plot? Like here?
Yes. Yes.
Or maybe, yeah?
No, the one that you were showing, actually.
Oh, the one I was showing, yeah.
Yeah.
Right. So the variable 7?
Yeah, which is really close, and it didn't quite reach the accuracy of 1. Did you make an ablation study of what kind of mistakes were happening there, what kind of errors you were having there?
Oh, right. This is a good question. So this is one of, this is a good question. So I'm just reminded of one direction that we completely dropped during the summer because we were just so confused by it. So, you can ask, like, do all those networks, do they make the same mistakes or different mistakes? Because if they make different mistakes, then you can boost. You can take a majority vote. And the crazy thing is that they have correlated mistakes. So there are certain Lego sentences, which is like plus, plus, minus. If you start with plus, plus, minus, they all make a mistake.
Oh, I see.
And we're just not able to understand this at all. So we kind of dropped it because it's just so mysterious. But we did try to see where are the mistakes coming from. And there is some correlation in the mistake. We're just not able to understand.
Interesting. Okay, thank you.
Sure. Okay, thanks everyone.